here to introduce Professor Cioaba from University of Delaware. His research interests are spectral graph theory, algebraic combinatorics through connections and applications to other areas of math and science. He got his undergraduate in mathematics and computer science at University of Bucharest in Romania. He got his PhD at Queen's University in Canada in 2005. I remember 2005. Many of you may not. He had postdocs at UC San Diego and University of Toronto, and he began in Delaware in 2009. He supervised many students and currently has 3 PhD students. He has over 70 papers and 2 books. He's an editor on multiple journals, big journals in linear algebra, and he has NSF-funded research right now, and he's been funded by multiple different funding agencies. So it's my pleasure to introduce him to speak about a brief tour of spectral graph theory.
Thank you very much, Tom, and thank you all for coming to my talk. Can you hear me okay in the back? Okay, awesome. So it's my first time in West Virginia, and I'm very happy to be here. I'm very honored that you have thought of me for this initiative. And I will try to give you, like the title says, a brief tour of this area of mathematics that's at the intersection of graph theory, linear algebra, and has application in many other fields. Yeah. Okay, so I'll start. We are professional mathematicians. We do research and we brag about the papers that we publish and so on. But I think the most important part of our job deals with actually teaching our students and trying to gear them towards interesting subjects in mathematics and computer science and the applications. So it's all about like trying to win their hearts and minds and trying to make them curious. And hopefully after that, the good things will come. So in that sense, this is a picture of the 2 of the kids in front, the smaller ones, they're my children. And my wife is a biochemist. She travels for work. So in some situations, she had to go for work. So I had to take my kids to class with me. And this is them and another friend of theirs in the undergraduate graph theory class a few years ago. And we actually did the 4-color theorem. And I asked them to come to the blackboard to color some dots or something like that. So that's what they are showing there. They're showing their work. So if you kind of, tune out now and wake up towards the end, that's what I'll show you at the end, what's on their pages of papers. What did they come up from this lecture I gave them about the 5-color theorem. So we proved the 5-color theorem, and I told them about 4-color theorem and so on. So they were younger then. Now the older one is the first year in high school, so it's a lot more difficult. So I'm trying to learn how to communicate with him and kind of try to keep that enthusiasm of mathematics. And I try to use similar techniques that I use to teaching my undergraduate students in my classes, even though the difference in age is quite large. So I will start with some basic notions. So you have a graph, and a graph is an abstract model of a network. And the simplest way you can think of it, you have a bunch of dots. You can think of it of drawing something on a paper or on a blackboard, whiteboard. You have some objects which are called vertices, and you can denote them by points, by dots on a piece of paper. And some of them are connected by edges, and some of them are not. So in that picture, there are 5 vertices, and those are the edges that I drew on the picture. And like I said, graphs are abstract models of network. You can model social networks, communication networks, biological networks, many such things. And they are studied in this area of mathematics called graph theory, which is part of combinatorics, part of discrete math. But also you can study them using linear algebraic objects such as matrices, and that's what I will talk about you today. So if you have a graph like that, the one in the picture with 5 vertices and 2 triangles joined at the vertex, you can associate to it what I call an adjacency matrix. And the adjacency matrix is a square matrix in which on the rows and on the columns, you put the vertices, the way you label your vertices. And then in the row X and in the column Y, just write down the number of edges that connects vertex X to vertex Y. So that's all it is. And now when you go from the graph in the picture to this matrix here, if you are aware of the labeling of the vertices, then you see that the graph and the matrix the information in those pictures are the same. So you don't lose any information going from the graph to the matrix. And if I have the matrix, I can draw the graph very easily. So there's no information lost there when you go from the graph to the adjacency matrix. But now adjacency matrix, you can study via tools from linear algebra. So the adjacency matrix has, when the graphs that I'll talk about here will be undirected. So there's no direction so if X is adjacent to Y, then Y is adjacent to X. And they also have no loops. So a vertex cannot be adjacent to itself. So the matrix that I get after I do this transformation from the graph to the adjacent matrix will always be a real and symmetric matrix. And from linear algebra, we know that the real and symmetric matrix will be diagonalizable, which is just a fancy word of saying that the matrix is similar to a diagonal matrix. And again, it means that you will have eigenvalues, n eigenvalues, including multiplicities. In this case, they will also be real, so I can order them from lambda1 to lambda n. And the n-dimensional space will have a basis which is formed by eigenvectors of this adjacency matrix. In this case, these are the eigenvalues. I computed them for you, and you see, like sometimes you have repeats, like -1 appears there twice. That's so now. Just remember, graphs and adjacency matrices. There's no information lost. They are essentially the same information. But when you go from matrices to eigenvalues, a matrix, you can think of it as an n by n object. So you have n squared, let's say, entries in there. Whereas when you go to eigenvalues, you're going to have n eigenvalues. So you will lose, it's not clear that it will be the same information. You'll keep all the information. So the game that we play here is, what information can I get from these eigenvalues about the graph that will tell me something useful about the graph? And vice versa, if I know something about the graph, how is that reflected in something about the eigenvalues of it? So I'll give you some examples about that. Now, let's go through some examples. If you have a regular graph, a deregular graph, is a graph in which every vertex has the same number of neighbors, which is, let's say, d. So in that case, if you have a deregular graph and you look at the eigenvalues of the adjacency matrix of this graph, again, you have n eigenvalues, and you can order them from the largest to the smallest. And it turns out that the largest will always be d. And that's not too hard to see, because if every vertex has degree d, then each row, if you sum up the entries in each row of the adjacency matrix, you will get the number d. So therefore, if you multiply the adjacency matrix by the all one vector, the resulting vector that you get collects all the row sums in it, and it will equal d, 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 which is d times the all one vector. So that shows you that d is an eigenvalue. And it turns out that something interesting happens here. It's actually all the eigenvalues are between minus d and d. And you will get minus d as an eigenvalue if and only if the graph is bipartite. So a graph is bipartite if you can split the vertices into two parts, sometimes called partite sets or color classes, such that any edge that you have will have to have an endpoint in one class and the endpoint in the other class. So this result, the second result, is the result that kind of people strive for in spectral graph theory. It's a result in which you have a combinatorial property being bipartite, which is the same thing as being two colorable. You can color the vertices with two colors, such that no edge has the same color on the endpoints. And it's equivalent with an algebraic property, which is about the smallest eigenvalue equaling minus d. So this is a kind of a good result to show to kind of understand kind of the meaning or what you're trying to do in spectral graph theory. It establishes correspondence between combinatorial properties and spectral properties. Now, the other thing, so I'll give you two examples here. The complete graph K5 will have eigenvalues 4 because every vertex is adjacent to 4, and you will have multiplicity 1. So I put the multiplicities as exponents, and the other eigenvalues are -1 with multiplicity 4. It's not too hard to prove this. The adjacency matrix of a complete graph like K5 will have 1 everywhere except on the diagonal where you have 0. So it's all one matrix minus the identity matrix, and you can calculate that. Another example I gave you there is a complete bipartite graph K33, 3 vertices on one side, on the left, 3 on the right, all of them adjacent. Again, this graph is 3 regular, so 3 will be an eigenvalue. It's bipartite, so -3 will be an eigenvalue, and the rest will happen to be 0. The last thing I'll mention on this slide is that when the graph is connected, you see I put everywhere the sign greater or equal to, except at the beginning between D and lambda 2, you can actually prove that there is a strict inequality there. And that gap between D and lambda 2 will be something that will come up later in the talk. And it will be important about measuring the connectivity and how good of an expander your graph is. So just keep that in mind. Okay, so I'll start with a problem from the 1960s. That's one of my favorite examples where you have a combinatorial problem that it's about graphs and so on, not so much about matrices. Well, actually, there's no matrix in the statement. But the only way that we can prove it, and the only way people have been able to prove it, is via like a linear algebraic method, via a spectral method using eigenvalue and eigenvector. So this is a problem related to what is called a Moore bound. So I'll give you, it's something more generally is true for diameter 3, 4, 5, and so on. But I'll give you here the first kind of non-trivial example. So let's say the motivation could be you want to build a network which is d-regular. So every vertex has exactly d neighbors. But you wanted to make it of diameter 2. So the diameter of the graph is the largest distance between two vertices. And the distance between two vertices x and y is the shortest path, the length of the shortest path from x to y. So if I tell you you have a graph of diameter 2, it means that if you pick two vertices, they're either adjacent, in which case the distance between them is 1. And if they're not adjacent, they must have at least one neighbor in common. So that shows that the diameter of the graph is 2. So the question that Moore asked, and this is an old question, is I give you a d and I give you a diameter. So I'll give you the example for diameter 2. How large can a graph of diameter 2 and degree of regularity d can be? And his argument is that the largest number of vertices you could have is you pick a vertex on the top, and then it has d neighbors. So those are the d neighbors on the next level, and each of them, if you want this to spread out as much as possible, so each of them would have d minus 1 neighbors, but all these neighbors at the level 2 should be distinct. And if you do the calculations, you will have 1 on the top, d on the second, on the below it, and d times d minus 1 nodes there. You add it up, you get d squared plus 1. So you cannot have more than that. So that is called Moore bound, and something similar holds in general if you replace the diameter 2 by 3, 4, and so on, but I won't do that here. But now, this is an upper bound. So it doesn't mean just because you have an upper bound of d squared plus 1 that there is such a graph. So he asked, okay, what are the d-regular graphs that are going to attain this bound? And this is the question that was studied by Hoffman and Singleton in the 1960s. And they proved something that looks a little bit like alchemy, some kind of numerology or something. So they proved that if G is a d-regular graph with diameter 2 and d squared plus 1 vertices, then d has to be 2, 3, 7, or 57. And of course, when you see the first time, you think, okay, 2, 3, 7, they're primes. 57, well, it's not a prime. Where do these numbers come from? So what they did was they said, okay, let's take this graph that has diameter 2 and it's d-regular and it has d squared plus 1 vertices. And what they did, they look at the adjacency matrix of the graph. And this graph is, in some sense, the most stretched out graph possible that you can make. And what they did first, they showed that graph cannot have triangles. So three vertices all with the edges between them. And that graph cannot have cycles of length 4. And based on that, when they looked at the adjacency matrix and they did some calculations, they found out that the adjacency matrix of this graph is going to have exactly 3 distinct eigenvalues. Now, the graph is d-regular, so you know that d is going to be one of these eigenvalues. And they calculated the other 2 eigenvalues, and you can get them in terms of d. And furthermore, they looked at these eigenvalues, and they calculated the multiplicities of these eigenvalues, because d will have multiplicity 1, and the other 2 eigenvalues, when you add up their multiplicity, you should get d squared plus 1 minus 1, which is d squared. And when you do the calculations, the multiplicities come up as a rational function. Now, I see students here, and I could ask you what's a rational function, but maybe it would be too scary. But it's some kind of polynomial over another polynomial. But I can ask you the different question. A multiplicity of an eigenvalue. What kind of a number it should be? Can it be -5? Can it be 3/2? Multiplicity is a dimension of a certain eigenspace, so it has to be a natural number. Or so their whole proof that D equals 2, 3, 7, 57 came from expressing the multiplicity of eigenvalues as a function of D, and then saying this multiplicity has to be an integer number, and the denominator should divide the numerator, because that's how it kind of works when you get the rational function. And when they did the calculation, there's some elementary number theory, and they came up with 2, 3, 7, 57. So yes, I mean, the idea is simple. It's there. Just calculate the eigenvalues and multiplicities. The technical details, if I had half an hour, I could show it to you, but it's best to make you curious about it, and maybe you'll go look it up. But again, this is a beautiful paper, Hoffman and Singleton, 1960s. It's in the IBM, so my journal of IBM. And now, you see, this is an implication. So D has to be 2, 3, 7, 57. But doesn't mean that there is such a graph. That's where there may be possibly a graph with these parameters. Now, when D equals 2, there is one graph that is 2 regular, and it has 5 vertices, and it has diameter 2, and that's a cycle on 5 vertices. That's not too hard to see. When D equals 3, you can get Peterson graph, which is 3 regular. It has 3 squared plus 1, which is 10, and is diameter 2. So that's also works out fine. And then for D equals 7, they actually constructed the graph, which has 50 vertices and it's 7 regular. Now this graph is called Hoffman and Singleton graph. When they constructed it, I think they call it graph G or something like that. They didn't call it after their names. And there is such a graph with these properties. This is a picture kind of from a later construction of the graph. You can construct this graph from 50 vertices by taking 5 cycles C5 at the bottom, 5 cycles C5 drawn in a complementary fashion on the top, and then there is a way to join them. This is a schematic description of a way that Neil Robertson from Ohio State constructed this graph. So there's some modular arithmetic, but I won't go through it. And then D57, this is one big open problem. Nobody knows if such a graph exists or not. So D57, if you haven't done it already, 57 squared plus 1 is 3,250. Nobody knows. I know people in these areas who are experts on many things, and some people think this graph doesn't exist. Some people think this graph exists, but we are not so smart to find it. I'm more on the side that the graph doesn't exist, because this graph on 3,250 vertices that has valency 57, if it exists, people have been able to prove that the group of symmetries of this graph is very small. It's something called automorphism group of a graph, which measures how much symmetries your graph has. So for example, the Peterson graph here, the automorphism group of the Peterson graph is the symmetric group of 5 elements, and that has order 5 factorial, it's 120. So a graph on 10 vertices has 120 symmetries. The Hoffman-Singleton graph, I don't remember it off the top of my head, but it also is very symmetric graph. The cycle C5, there's something about dihedral group, also like large compared to the size. But for this graph on 3,250 vertices, some smart people have been able to prove that if it exists, the automorphism group should have order less than 300. So that kind of tells you that if the graph would exist, it would have to be not so nice, not so symmetric. But no, again, nobody knows if the graph exists or not. If you look on arXiv, there are several papers by some mathematician claiming that he proved that the graph doesn't exist, and the proofs turned out to be wrong. And then now if you go to the webpage of Andreas Brouwer, who's a mathematician in Netherlands, he actually wrote one document in which he explains why all of these proofs are wrong. So again, this is a hard question. One joke I like to say, if you're a professor and you work in this area, and if you have a student that maybe you don't like so much, that's a question. That's a question that you want to give them, because it's a very simple statement and so on. But it's actually, so be careful when your teachers give you too easy questions. Okay, so yeah, so that's a hard question. Now here's a question where this is one of the topics that it's one of my favorite topics to give undergraduate students to do research. because it's something that they can do by hand for many examples. So it's a question about addressing of a graph. So you are given a graph, let's say a network, and you want to give vertices some kind of labels or call addresses, such that if I give you two vertices, I look at their labels and I know how to get from one to the other by a shortest path in just by looking at the addresses. So one obvious way would be, let's just give them addresses which are binary vectors, so vectors of 0 and 1. And that's what I try to do on the left, and that's the cube. And the cube, by definition, the three-dimensional cube, and you can go to higher dimensions of the cube, you can label the vertices by 0, 1 vectors, in this case of length 3, such that two vertices are adjacent if and only if their words differ in exactly one position. And by this definition, this will help you to show that in the cube, you give me two vertices, I just look at their words, like if you give me 3 zeros and 3 ones, they differ in all positions, so I know that the shortest path between them will have length 3. And using these addresses, I can actually, if I want to send a message from 3 zeros to 3 ones, I know how to do it from these two vertices. Unfortunately, what happens is that not all the graphs, you can address them using 0, 1 words. So the simplest example would be a triangle. If you have 3 vertices, you can give one label 0, one label 1. What do you do on the third vertex? Because you want these addresses to tell you the distances between the vertices. So Graham and Pollack, they were working at Bell Labs in the 70s, and they came up with this addressing. So you have a graph, you have a set of vertices, and their addresses is not just using 0, 1. You're using another symbol called star over some length k, let's say. So you want to create such a addressing such that the distance in the graph between any two vertices, so the shortest length of a path from x to y, equals the number of positions j where one word has a 0 and the other one has a 1. So how do you interpret this? The way you interpret is that this symbol star can be at the same time a 0 as a 1, and it helps you in the situation that for any graph you can actually find something like this. So that's one thing that they proved. And then they were interested in they had a way of finding such addressing for k large, and they asked, okay, how small can k be? And they denoted this parameter k by n of g. We don't know now. I believe that determining this n of g should be like one of these NP-hard problems and so on, like millennium problems, but nobody has ever to prove it. So, okay. So again, the problem here is I give you a small graph, find these addresses on the vertices with words of the same length of the alphabet 0, 1, and star, such that the distance between any two vertices equals the number of positions. One has a 0, one has a 1. So the example on the right, you see that's the complete graph on 6 vertices. It has triangles. So the addressing that I gave you there, it uses these stars, and it's optimal because the length of it is 5, and you cannot find anything with shorter length. 5 is the shortest. But that actually is a non-trivial result. So, okay, so here's what happens behind the scenes. So what's the deal with this addressing? So the addressing, what happens is essentially a decomposition of something associated to your graph. So if you have a graph G, think about the graph, the small graph on 3 vertices on the left, that path on 3 vertices. I can create what is called a distance multigraph of it, which has the same vertices, but now between any two vertices xy, I put as many edges as the distance between the vertices xy. So if in my graph G, x and y were adjacent, then the distance between them is 1, so that edge stays the same. But if the two vertices on the left there are not adjacent, the distance of them in the graph G is 2, so then I put 2 multiple edges on the distance multiplier. Similarly, if I have the complete graph, on 6 vertices as before, in the complete graph, any two vertices are at distance 1, so the distance multigraph of the complete graph on 6 vertices will be the complete graph on 6 vertices. So then, I won't prove this here, but essentially, an addressing of length k, the stuff that I showed before, the 0, 1 star business, is equivalent to partition this edge set of this multigraph into what are called bicliques into k biclicks, a biclick is a complete bipartite graph. Complete bipartite graph, a bipartite graph, I told you what it is. Vertices on the left, vertices on the right, any edges only may go between the two parts. When you have all the possible edges between the two parts, that's what it's called complete. And this is complete bipartite K3, 3 on here, 3 on here. This is complete bipartite K2, 3, 2 and 3, and that one is K1, 4. You have 1 on one side and 4. So this addressing, it's the same thing as a partition or decomposition into this complete biclicks. And using this fact, somebody proved this lower bound. So this is Graham and Pollack attribute this to Witzenhausen. And this is essentially the benchmark and the best lower bound that we have in general for this parameter n of g. And it comes from linear algebra again. So you go through this n of g, you go through this decomposition, this partition of the multigraph. And when you have a partition, what happens is that translates into a certain matrix equaling the sum of other matrices. And then you do a little bit of linear algebra, from which you can deduce that this parameter will always be greater or equal than the maximum of the number of positive and negative eigenvalues of, so here I'm abusing a little bit the language. D will be the distance matrix of the graph, in which you have square matrix, row X, column Y, you put the distance between X and Y. So for the complete graph, the distance matrix will be the same thing as the adjacency matrix, the one with all ones and 0. So this is the explanation here. The distance of this Kn will have these eigenvalues. And so you have one positive eigenvalue, and you have technically n minus 1 negative eigenvalues because you consider multiplicities. So when you do the maximum between them, this is this lower bound from the theorem will be n minus 1. That's why I told you before that for K6, this parameter will always be at least 5. That's the reason. And then you can construct an addressing with that length. So this theorem is, again, another theorem for which the only proof that we have is using this linear algebra method. Like, we don't have a combinatorial proof. And people have tried to do it, but nobody has been able to do it. Now, on the other end, Graham and Pollack, I told you that they proved that n of g is at most the diameter times n minus 1. And then in the 80s, Graham made a conjecture, and I think he put money on it, something like $200 or something. And yeah, I mean, I don't know if you're a student and you make conjectures, don't do that, okay? So, but shortly after that, Winkler proved it, and he proved that for any graph, this parameter is at most n minus 1. There are graphs for which it's not n minus 1, so you cannot, and this is what is called Graham's squash cube conjecture. You can find it, it's a short paper. And it's actually, if you like things that come maybe from math and computer science, like breadth first search, depth first search in a graph, that's kind of the methods that Winkler used to this. Okay. So this parameter, what I did for undergraduates, you have a family of graphs, and you just say, okay, here's the game. Can you find addressing of these graphs, optimal addressing? And we did this. We have a paper, Discrete Applied Math, in 2017, and this is Michelle Markiewicz. She was an undergraduate at Delaware, and I'll show you some of the pictures that she has there on the poster. So University of Delaware has this very nice program called Summer Scholar, in which the students can do research over the summer for 10 weeks, and they get paid $4,000 or something like that. And so we did quite a bit in this situation. So I'll show you some of our results. So Michelle did this work, and then the summer after that, I wanted her to work with me, but she got accepted into this NSA summer director program. And from there on, after she graduated, she now works at NSA as a mathematician. And so what we did is for these graphs, which are Hamming graphs, for now, we just consider in the picture, I just have the ones that have d equals 2. So think about like a grid. In this case, the one on the left is H23, the one on the right is H24. So the graph would be, you have this 3x3 board, everybody on the same row or on the same column are adjacent. And the optimal addressing is given here. The length of it is 4. And that's the same thing over there on the right. Optimal addressing is length 6, I guess. And so we did this for all of them for DQ. For all these Hamming graphs, you get this bound. And there are two parts of it. So this parameter, you have to find a lower bound. And the lower bound, we found it from linear algebra. And I'll tell you more about Hamming graphs in the talk tomorrow. But in the this is the eigenvalues that you get for this distance matrix. You get one positive, you get 0 with a huge multiplicity, and you get a negative 1 with a multiplicity dq minus 1. So that's a lower bound there. And then we came up with the addressing of the same length, and that was approved. And then there are other graphs of interest, which are called Johnson graphs. And again, I'll talk more about them tomorrow. You have two parameters, J and K. You have a set with n elements, and the vertices are going to be all the K subsets of that set with n elements. And they're adjacent if they overlap in the intersection between them is size K minus 1. If K equals 1, this is the same thing as the complete graph on n vertices. If n equals 2, this is the same thing as a line graph of complete graph Kn. And here's a picture of J52 and N542. And we did, so here in the same paper, if you do the eigenvalue business, you get a lower bound of n minus 1. And then you analyze the equality case and you show that it cannot happen. So you can move the bound to, but also from her work in some collaborators in 2007. So later on, I had another undergraduate student working over the summer, Brendan Gilbert, and we did more work with him. He was really good with computers. So he could write all these very nice backtracking algorithms to look for addressing. And so these are the things that we did with him. We did this in general for J and K. We have a way to address with at most K times n minus K, which I thought it was sharp all the time, but it's not sharp for this n equals 6, K equals 3. And then with our other collaborators, we wrote this paper that it's in experimental mathematics. And we proved that most of these graphs, n of g, if I show you the upper bound before n minus 1, it turns out that most of them are going to have even smaller addressing, but we don't know the exact, we don't have good lower bounds for n of g. This goes in another area of graph theory, random graphs, and we don't know how to get better lower bounds there. But again, this is I find it interesting because again, it's a mathematical program with a problem with a pretty good motivation from my point of view, on which students can do some work on their own independently, and they can learn more graph theory, more linear algebra, even probability, and so on. And I think their experience at university would be enriched from working on this problem. Now, this is the hardest problem in this area. Again, it's maybe not on par with the 57, 300, 250, but if you're thinking about addressing graphs, these are the hardest ones for which we don't know what to do. And these are called cocktail party graphs. The simplest one to the ones on the top, n equals 2, n equals 3. You have a complete graph, and you remove a perfect matching. So you like if I have a complete on an even number of vertices. So on the one in the middle on the top, I have 4 vertices, and I remove the 2 parallel edges. The one to the right, I have 6 vertices, all of them adjacent, and I remove this matching of 3, 3, and so on, 4, and so on. It's hard to see 4. And this problem was studied by Zaks in 80s with some kind of geometric motivation. And he obtained these upper bounds of addressing about 3m over 2. And he obtained a lower bound just from eigenvalues of m plus 1. And later, Alan Hoffman. So Alan Hoffman has a paper in 2001, which is called On a Problem of Zaks. And that's what he does. He improves his lower bound. He adds this thing. So he analyzes the equality case in linear algebra. But this is a problem where the construction doesn't match the lower bound from linear algebra. And we don't know how to, I believe that this is the right value, but nobody knows how to bring that up. So these are very simple graphs, complete graph minus a perfect matching, but nobody knows what. So this is
What's called a cocktail?
So the story is that there's supposed to be n couples, and they go to a dinner, and nobody at the dinner wants to talk to their partner. So that's represented by the perfect matching that you delete. So yeah, that's a cocktail party. Yeah. Okay. So let me tell you about other graphs with names. So this is related to other thing I did with undergraduates. So these are called pancake graphs. So I know it's after lunch and you may get hungry, so just okay. So okay, pancakes. Okay, here, what are pancake graphs? You can think of them as having this stack like the ones here on the in the center. You have a stack of n pancakes. In the picture, there are 3, and what from this configuration that you have there, so the pancakes don't have the same size. So from this configuration, you take the spatula, you put it under, and you flip the thing on the top. And what other configurations can you get? So the one on the top left corner, 0 flips. You leave it as it is. And then if I do, for example, if I put the spatula at the bottom and I flip the whole thing, I get the one over here. Or if I put the spatula between the first and the second pancake and I flip it, I get, that's what the meaning of 1 flip is. And the meaning of 2 flips and 3 flips is you do another flip after that and you flip it. Now, if you want to be fancy, and that's kind of what we want, is you represent these pancakes by permutation. So the permutation, like an identity permutation, would be the corresponding to this one on the top left. But over there, I have them on 4. So it'll be 1, 2, 3, 4. And then the flip, what it does in terms of permutation, you take an initial segment on your permutation and you reverse it, and that would be the neighbor. That represents 1 flip of the pancake stack. So 1, 2, 3, 4. If I put the spatula at the bottom and I flip the whole thing, it's adjacent to 4, 3, 2, 1, which you see to the right. But you can put the spatula into 2 other positions and you can get different permutations. So you get, this is called the pancake graph. And it's a graph that was studied by Bill Gates when he was an undergraduate. Yeah. So one question that people ask that they don't know the answer is the diameter of this graph. So, you know, what's the shortest path in these graphs between 2 vertices? And this red stuff, to match the red stuff, this is what Bill Gates and so Christos Papadimitriou now is a famous professor at that time he was at Harvard, now I think he's at Berkeley. And so they proved the bound in red. And now this graph, the number of vertices for general n is n factorial because it's a number of permutations. So it's a very large graph, but the diameter, it's linear in n. So it's laterally this. And then there were improvement on the lower bound here, and improvement by the same authors there. But this is still a very, open. Yeah, I wouldn't give this to the students because many other people have worked on it, but they're related graphs on which you can make progress. But still, it's again an example of one of these simple questions where, okay, what's the answer? What do you do? So again, if you want to be fancy, you can call this pancake graph is a Cayley graph of Sn with n-1 generated. So Cayley graph is if you have a group, like in this case, all the set of all permutations with n elements, that's a symmetric group Sn. Okay, and then you make 2 of them adjacent, 2 elements of the group adjacent. If you multiply one by the inverse of the other, you get an element of a given set, and that given set is the set of permutations that I put at the bottom. And so this is a Cayley graph, so you will have n factorial vertices. Each vertex will have n-1 neighbors, and people look at these graphs of interest in also from the algebraic point of view, and it's easy because it's an n-1 regular graph. Largest eigenvalue is n-1, and then it was work done by Sesi in 2009 using like some representation theory, and Zhang and Tobin using more elementary methods. You prove that the second eigenvalue is n-1. So second eigenvalue is of interest here. So this is a work. So this is me on the left. This is before COVID, 2019. So from the right, that's a student from NTU in Singapore who visited me for half a year, Zhao Quang Tan, who was on this paper. And then that's Brendan Gilbert next to him. And this is Noga Alon, who is at Princeton in the fall. And we always invite him to come to UD. And we were very happy because, you see, on the blackboard, we told him all the questions that we couldn't solve. And he spent half an hour thinking about them, and he couldn't solve them. So that was for us a big victory. if you work with people like this, you will see like Noga alone is amazes me all the time, because any math problem you tell him, he will know how to do it better, how to solve it. He knows everything that you thought about it. So some people have amazing, he has written over 600 math papers, and 1,000. I'm sorry. Yeah. So like that. In the meantime, there are 400 more. So yeah. So what we did is we looked at some of these flip graphs, and the flip graph that we looked, it wasn't a pancake. It was a flip graph on perfect matching. So it's kind of, again, you have n in this picture. N is 6, and what I draw there are all the perfect matchings. I think there are 15 perfect matchings on 6 vertices, and 2 of them are adjacent. If you have a perfect matching, you have 2 edges. You pick 2 edges. They're like this. Just change them to be parallel like this, or change them to be diagonal. So that's a flip. So in general, there is a general notion of flip graphs in math and computer science, in which you have some configuration and you have some set of objects, and 2 of them are adjacent. If one of them is obtained from the other by doing something called flip, which differs. Like the flip could be flipping the pancakes. Here you just flip the edges. You just change the edge. And these things, people use them because, for example, in like theory of probability, random walks, and so on, you are interested in generating some of these objects at random. And then one way you can do it, you construct this flip graph, and you do something called a random walk or something, and you can analyze the behavior of that, and that gives you what you need. So here, these flip graphs were studied again by Diaconis and Susan Holmes, and they studied from this perspective of random walks, and there are connections between these flip graphs on perfect matching and phylogenetic trees. Other people in graph theory study them as well. And one question that they ask, these people ask a very simple question. Okay, chromatic number, how can I color these vertices in this flip graph? And they notice for 2, 3, 4, which is small enough that you can do calculations, you can see like the number of vertices is 2n minus 1 double factorial, which is not 2n minus 1 factorial and then again factorial. Is the one where you go down in steps of 2. So 2n minus 1 times 2n minus 3 times 2n minus 5. Because we'll be really in trouble if we put factorials like that, because that would be really large. So that's why here n is 6 in this picture. So 2n minus 1 double factorial will be 5 double factorial. So 5 times 3 times 1 is 15. And the degree is n times n minus 1. So on this picture, the degree is 3 times 3 minus 1 is 6. So you can calculate these things. So they have this thing about the chromatic number. They, we always make fun of the engineers. Yeah, do you have a question?
I was going to ask, is there any way to prove how many axes of symmetry the sort of graph has? Since you mentioned axes of symmetry for similar graphs earlier, but
so how you determine like the automorphism group?
How many symmetric?
Yeah, so I guess one way you can try to do is you have your graph description, and you can try to give a description of, well, this permutation of the vertices is going to preserve adjacency and preserve non-adjacency. So that's the thing. Like, for example, on a cycle, if I give you a cycle, whatever vertices you want, if I map every vertex to the next one on the cycle, you pick, let's say, from my perspective, it's clockwise. Maybe from yours it's different. But if you go clockwise and you map vertex 1 to vertex 2, vertex 2 to vertex 3, vertex 3 to vertex 4, and so on, you go back, then you notice that anytime you have 2 adjacent vertices, their images are also adjacent. And anytime you have 2 non-adjacent vertices, their images are also non-adjacent. So this permutation is an automorphism of the graph. And so you go and you collect as many automorphisms as you can find. And then when you stop collecting them, you say, well, maybe these are all. And then you try to prove that there are no other automorphisms. So that's kind of one way of doing it. So some graphs, like I didn't tell you about Peterson graph, but the Peterson graph has a natural symmetry because the vertices can be labeled with pairs of elements from the set 1 to 5. So yeah, that's kind of. Yeah. But here, anyway, so here they prove, I was at my joke about engineers, but yeah, people in math, they say, oh, the engineers notice something for equal 1, 2, 3, so they believe it's true for, but mathematicians do this all the time. So this is the case. They notice something for 2, 3, 4, and conjecture that is, they conjecture that is true, that the chromatic number is n+1, and then they gave an upper bound of for n, and with the undergraduate and with Gordon Royal, we can actually get better, but we couldn't prove their conjecture. Well, we can color the graph. So if you have a perfect matching, you embed it into some finite field, and you do something, and you can prove a upper bound of 2n. And now the stuff that may be interesting for students that like computations and so on. So Gordon Royal, our co-author, he's brilliant with computations. But again, just to show you how quickly these graphs grow, see n equals 5. What did I say? 9 double factorial. 9 times 7 times 5 times 3, 945 is 20 regular. And I couldn't do it by hand, but he could do it by computer. And the code is there. So it's free for everybody to play with and so on. And the one on 6, it has 10,000 vertices. It's 3 regular, so it's a very sparse graph. But we can, he can color it with 7, and again, the code is there. But we don't know if this is actually equal 6 or if this is actually equal 7. So these are questions where we pushed it as much as we can with this undergraduate, but hopefully other people will come along and try to do something about them. But again, there are questions where, like I said, undergraduate students can make a contribution by learning about it and being curious about that. Now, there's another version of this. Maybe I'll skip it a little bit. This is similar to the pancake where you reverse. So from this work, we went down another rabbit hole, and we ended up with this what I call sign reversal graphs, which are graphs kind of like the pancake graphs, but with this weirder adjacency matrix, definition. And here again, we ended up with some things that we can prove in only certain ranges, but we couldn't do it. Let me tell you about one other interesting thing where eigenvalues play a role. This is this expansion constant. So if you have a graph, one way of measuring how connected the graph is to, take all possible ways you can break the vertices into 2 parts, calculate the edges between the 2 parts, and take the minimum. That's called edge connectivity. And that's what I mean by the numerator on the top. A is a bad notation here, but A is not adjacency matrix, it's a subset of vertices, a cardinality at most half. And now there is this parameter called expansion constant, which takes the minimum of this expression of this ratio over all subsets of vertices. So if A here has 3 vertices, then the denominator is 3. And the numerator, what it counts these edges where you have a vertex in A and the vertex outside of A. So you start counting all these edges, 1, 2, 3, and so on. And you take the ratio, but now you have to minimize this quantity over exponentially many subsets of vertices. So that's a bit of and this is called expansion constant. And people are interested, especially in computer science, but also in mathematics, about expanders. I will go a little bit quickly about it. Again, the problem boils down to eigenvalues of graphs. And the question that has been done here recently, it essentially, this is a big breakthrough. If you have a graph which is irregular, the question that they solved is, I can change some of the ones on the adjacency matrix to -1, such that the largest eigenvalue of the graph that I have is at most 2 square root of d minus 1. So again, that could be something that you pick your favorite graph, Peterson graph or something. You have the adjacency matrix, change some of the ones to -1 such that you minimize the spectral radius. And this is serious business about sign adjacency matrices and 2 square root of d minus 1. And it's relates to this notion of 2 lifts, which I'll kind of skip through it here. But all I wanted to tell you is that this sign adjacency matrix is another important part of spectral graph theory, where recently there's been progress in solving this big conjecture in computer science, which is called sensitivity conjecture. You take the n-dimensional cube, you take more than half of the vertices, you have to show that one vertex is adjacent to square root of n of them. These are the cubes. And the previous bound was done by these big shots, and it was log in base 2 of 10. And then Hao Huang, who was an assistant professor at Emory, solved this problem in 2019, and the proof of it was given in a tweet. and that's the proof. This is Ryan O'Donnell, is a professor at Carnegie Mellon, and so the proof is, so you take more than this many vertices in the cube, you vertex. So what they did first, Hao Huang, for the adjacency matrix of the cube, that he found this 1 minus 1 sign adjacency matrix with all the eigenvalues square root or plus or square root of n or minus square root of n. And then he used something which is called eigenvalue interlacing, which is if you have a big symmetric matrix and you delete some rows, delete the same columns, the matrix that you get, the eigenvalues of it are going to go in a certain gaps between the eigenvalues of the big matrix. That's called Cauchy interlacing. And that's basically the second part. And in a subgraph, so yeah, I mean, the math of it, there's a lot of details hidden here, but nevertheless, I mean, I'm jealous that he could actually do it in a tweet. Like he, that's brilliant. So this was a big result, and I encourage you undergraduates to read it because like I did one exposition for our math newsletter, and you can find this, just Google Hao Huang sensitivity conjecture. It's full of it, and you can find many resources, and it's a beautiful result, and it has spun a lot of research. Like many people are looking now into the sign adjacency matrices. So anyway, I'll skip this stuff that we did. Let me show you this. So this is on the left. This is the younger one, our younger son. Here I was trying to explain the notion of a face in a planar graph and so on. He has to work a little bit on his calligraphy, but there's an E equals V plus F minus 2 on the top. So they got the gist of that and some graphs. And on the right, I think that's my older son, and something about 4-color theory. He put his name on it, so he gets graded. So that's good. You always, put your name on your test, so you get credit for it. But then at the end, yeah. So I'll stop here. I'm sorry for going over time. Thank you.
Questions? We have time for questions.
Yeah.
So, if a student wants to get into this kind of topic or to start working on this, so what kind of classes or what kind of background you would encourage them to?
I mean, so if they have some experience with proofs, that's always good. Like to just do a intro to proof class if you have, and then if you know linear algebra, that's always a plus. The graph theory part, it helps if you know something before, but you can always learn it on the fly. So with the students that we take in the summer, the first part of it is mostly just going through, like we teach them a lot of stuff. So that's what you spend some time doing. And then when you do the work with students that are motivated and they're eager to learn new things, you can get a lot of mileage because you can teach a little bit and then you can give them homework, you can give them exercise, you can give them stuff that they can try. And they can try stuff on mathematical content, but they can try stuff on computation stuff. Like there are all these programs like Sage Math that is freely available. So there are a lot of graphs are already built in there. So you don't have to build it yourself. And you can just play with it and try to see this graph, visualize it. What is this parameter? What is that parameter? So that would be mine. So make it more at the beginning, kind of like a game, but it's a fun game. So hopefully you'll get them to do that.
Okay, other questions? Yeah.
Back early in the talk,
Yeah.
you had this idea of graphs of diameter 2.
Yeah.
And then you had this d squared plus 1
Yes,
vertex.
yeah.
And then you said if you change the diameter, then you get a different polynomial. Can you say something?
Yes, so you can do, remember like the bound that you get is the maximum, this more bound, you obtain it by taking a vertex, d neighbors, d minus 1 neighbors for each of them. If my diameter were 3, the bound changes to a vertex, d neighbors, the second level as before, but there's a third level where each thing gets, each vertex gets d minus 1. So you get to something like, it's a geometric progression. You get 1 plus d times d minus 1, and then you'll get another term plus d times d minus 2. So that's the general Moore bound, and it works for any diameter. That's the upper bound. Now, what happens is for diameters which are 3 or more, some people in the 70s, independently, Japanese mathematician Banai and Ito and Damerel, they proved that you will never have equality for diameter 3 or more unless your graph is an odd cycle. So for the cycle, that's why I keep the valency 3 or more. Cycles will satisfy this property because you will have a vertex cycle and so on, and odd cycle will satisfy it, but odd cycles are somewhat simple. So other than that, you won't touch that bound for any diameter 3 or more. I mean, now there's like in a lot of research into this, how close can you get to the bound? And you can prove results. Your order of your graph is at most a more bound minus something. And then how big, what kind of graph can you construct? So if you're interested, there is this journal, which is the first electronic journal for combinatorics, which is called the Electronic Journal of Combinatorics. And it has a section which are called dynamic surveys. And one of the dynamic surveys is on this Moore problem. And they give you all the history and all the information, and they can tell you stuff that I don't know off the top of my head. If I give you degree 5 and diameter 7, what's the largest graph that somebody has constructed with degree 5 and diameter 7? Dynamic survey, so these things are freely available online. And dynamic survey means that the authors update the survey regularly and tells you their last update was done on, 2020 or something. So they're very useful because it's a state of the art, like but up to that point.
We got one question from online. They asked about your summer research program that you talked about, and they asked, do you take students from other schools?
I mean, I wish we could, but I think it's something that
Internal.
Yeah, University of Delaware offers to our undergraduates, and it's mostly done. So at UD is done by, I think many other schools do it, but at UD, mostly done based on GPA and like some letters. Like if the students do well in some class, that's what I tell them. Just do well in the class and ask the professor that was teaching that class if they do summer scholar, and then try to get involved. I think it's almost like an internship. I mean, it's still like you're dealing with theoretical questions, but you find out what if research is for you or not, because you end up, I mean, if you have like a graduate program, you end up many times with students that they didn't know, okay, do you really want to do grad school, or it's kind of an inertia? Okay, I didn't have plan B and I ended up being in grad school. So if you're an undergraduate, I think it's very useful to try these things, try to apply for REUs, if there are schools around that offer these NSF REUs, and try to look for these research opportunities, because they're very useful. You'll find out if research is something that you want to do, or maybe you want to do something else. And the sooner you find out, the better you are, I think.